About the week, do you know the week in terms of just general map schedule?
Yeah.
Okay, so I will not see you tomorrow, I will see you Wednesday. Wednesday will be a long period. Oh, I should have made the test that day. And I could have gone really long on the test. Okay. Too late. Well then, at any rate, here's your idea. Your review 8 is today. I don't see you tomorrow, Tuesday, and review 9 and lunch are Wednesday. Your lunch is not based on me, though. Your lunch is based on your 6th period, so that's not my issue with you. I'll see you Wednesday then, and by the way, there still are 7th hours. In fact, they're even longer, so if you wanted to come in 7th period tomorrow, I could see you. But at any rate, the test is Thursday, and I'm thinking through review 7. What do you think? Through last week's material. Sound good?
Yep.
Okay. So just show up and be brilliant that day, and everything will be great.
Are you gonna have a review before school on that?
I don't typically do that in BC. So no. Although if you want to just drop by for questions, I'll be here for sure, but I don't have this pressure.
Okay.
Nor is there any extra credit in this class. Pretty much. So, that said, you best just learn what you want. Did Miss Cannon do review sessions before? She did?
Yeah.
Were they productive?
Oh, yeah.
I will rethink that, but maybe I will. How did she fight the temptation to teach you what was going to be on the test ahead of time? Did she
went over the review that she gave us. She would like give us a review.
She gave you a review for the test?
Yeah.
Oh, I definitely don't do that. That's crazy. Yeah, I'm not doing it. That's crazy. That's nuts. No way.
Giving us a review.
I can think of 0 professors that ever gave me a review for a test. Never. Maybe for the final, but never for. Well, maybe for a midterm. I don't know. That feels like
It's so you know what to study.
I'll tell you what to study. Everything you ever learned. Study. It's called the comprehensive exam. When you go to get your master's, you'll take what's called a comp. Okay? Now, imagine if before you graduated high school, they said, we're going to gather a few questions from every teacher you ever had in all 6 years, and then you're going to take a test on that stuff over 5 days. Wouldn't that be fun? Really fun. And that's a lot to study, 6 years of material. Well, that's what comps are. Yes?
Will we get back like 3 problem sets?
Yeah, right here. I'll have it graded by then. Here's graded what I have. And yes, I will make sure I have stuff graded for you. Here you go. Boom. By the way, review 5 is in there, but I didn't get to all the questions on review 5, so if you didn't turn in review 5, not to worry, it's not late. I just got it from some people, so I graded what I had. But if you're turning review 5 in today, that's fine. Okay. I guess I need to think about whether I can get a review together or not. So maybe we'll review in class, since it's a long class, maybe we could just review in class Wednesday.
Can we play bingo?
That also takes a while to work. That might be fun, but we'll see. I promise you nothing. Throwing you a bone, just so you're aware that I'm throwing you a bone. These 3 examples that are in the notes before, I actually had on the homework, but I thought, let's move them to the notes rather than do more practice problems. Let's just do some together, take them off the homework. So your homework is a little light, considering that homework is what, maybe 9, 12, whatever problems, and it's 2 days, that shouldn't be too bad. By the way, on the one on the back, where you're cutting out squares of a piece of paper to make an optimum box, yeah, I really expect you to make a box. Okay, it's always good It's always the issue every year where the kids get home and say, I don't know if you really wanted to me to make an actual box. Yeah. On Monday, you will be bringing in a box. Or on Wednesday, you will be bringing in a box of paper. Okay? Okay. Those of you that are going to be engineers, I got to tell you, I worked with a guy that, he worked with engineers at Coors. He was the actual guy that made the stuff that they designed on paper. And he would often say, these guys have no idea what will actually work on it. The theory is different than the lab. This one, you can't make this actually in the lab. So it's my goal that you get a little feel for this stuff that you make on paper, that you design on paper actually has a real life 3D structure to it. And I don't want you to be a knucklehead that doesn't know how that connects to the actual physical. So that's why that's there. Looking at the old lessons, this is pink because applications of the derivative are usually a totally different idea. If I asked you, hey, use the product rule to take this derivative, well, that's a derivative technique. But if I say, hey, where does this thing have a maximum? Well, that's using the derivative idea that you take to apply it to finding something. That's an application problem. We talked about the first derivative the other day. First derivative test. This is the second derivative test. And in retrospect, I think the notes, I didn't give you notes the other day. That's why. Never mind. Okay, so that's why these are pink. New chapter. All right, here we go. Second derivative test. Do you remember this? Oh, not the second derivative test. Do you remember what the second derivative tells you about the concavity of a graph? Concave up or down. If the second derivative is positive, then it's concave. Why is that? Because you memorize that, or because there is an actual real-life reason? Why would something be concaving up if the second derivative is positive? Let me say it this way. I'll lead you. If the second derivative is positive, the first derivative is? Say that again. If the second derivative is positive, the first derivative is? Changing. Now you're getting somewhere. Changing how? Up. What? You're killing me. Changing up. I'll say it again. If the second derivative is positive, the first derivative is changing in a positive way. Therefore, increasing. If a derivative is positive, the thing is increasing. If the second derivative is positive, the first derivative is increasing. If the first derivative is increasing, then the slopes of the original graph are increasing. If the slopes are increasing, then the curve will concave up. Wow, that was painful. Gracious. Okay, so now, here we go. We're going to find where the curve is concave up or concave down. In order to do that, I will need to focus on the second derivative. Let's start with the first derivative. What is the first derivative?
Negative 3x squared plus 6x.
Negative 3x squared plus 6x. Do I need to set that equal to 0 and find where that's 0? For this problem.
Not for this one.
Not for this problem. Do I sometimes need to posit the first derivative, set it equal to 0, and solve for critical numbers? You do. That's when you do the second derivative test. You'll need to pause and find critical numbers. That's the next example. For now, I don't care where the first derivative is positive, because I don't care where it goes flat. I just care where concave up, concave down. So I'm going to go second derivative. Second derivative is?
Negative 6x plus 6.
Negative 6x plus 6. Okay. To find where the second derivative is negative or positive, the great dividing line between those is?
0.
0. So we need to set that equal to?
0.
0. Second derivative hits 0 at x equal?
1.
1. Therefore, it must be positive or negative everywhere else. What is the sign of the second derivative before 0 or at x is less than 0? Positive. For example, at negative 1, you'd get positive 6 plus 6, that's positive. And after 0, like at 2, you'd get
Negative.
negative. Now, answering the question with justification. The graph is, because I'm a knucklehead. Just check and make sure you're paying attention. Way to go. So, y, or the graph, is concave up. Remember, we're talking about the original graph, not the first derivative graph and the second derivative graph. So y is concave up on what interval?
Negative infinity to 1.
Negative infinity to 1. I'm going to say not inclusive because it's neither concave up nor down at 1. Because second derivative is positive or greater than 0. Y is concave down, and you may abbreviate concave up, concave down in my class and on the AP test. Can't really remember if professors cared. You'll have to fill them out on that. Concave down on 1 to infinity because y double is less than 0. All right, what about inflection points? They're where the graph does what? Changes concavity. Okay, so would you please write this in terms of notes? Inflection point where y double equals 0. Write that. Do you have that down? Okay, then put a big old X through it. Not true. Inflection point where y double changes sign. Okay. Give me an example of a function where the second derivative would be 0 at a point, but you don't have inflection there. X cubed. You do have an inflection point there. Try again. X to the fourth. Thank you. X to the fourth. Y equals x to the fourth surely has a second derivative 0 at 0. Yes? And yet we know that that is a square. It will not change sign there. And the graph bears that out. There is no inflection point. So please don't fall into the goofy trap of saying it's where the second derivative is 0. It's not true. Do you start looking where the second derivative is 0? Is that a good candidate?
Yes.
Yeah, but you have to go further and verify that it's actually changing signs. Okay, now, did I answer the question? I did not. So the coordinates, where are the coordinates of the inflection point? Actually, where's the inflection point x-wise?
1.
At 1 what? 1, 2, and justify, because y double prime changes sign there. Now, in the first derivative test, you have to be very specific about how it changes sign. Negative to positive for a man, positive to negative for a man. Do you have to be specific on this?
Not for this one.
You do. Okay. Questions there? Yes?
Do we have a point or can we just say x is x?
I would normally say x, but I took care to put coordinates in here, and so because I said coordinates, you do need that. Okay? If they just said find where there is an inflection point, then I could probably sufficient. Good question. All right, example 2. Going a little bit further and using the second derivative to identify extrema, or extrema, depending on what part of the country you're coming from. So, what would you do here? Okay, derivative. What is the derivative? Okay. Pause there or go on to the second derivative?
I mean, I saw it for this first.
Yeah, we do need to find the critical numbers. So, solving that, maybe a greatest common factor of 4x squared would be delightful. And where are your critical numbers?
0 and 3.
0 and 3. Okay, now reading the instructions carefully, it says, using the second derivative test if possible. Why does it say if possible? Second derivative test doesn't always succeed. Consider this case here. Actually, we need to actually do the second derivative test first before how it works before we get to that. So let's go on. Let's say we now find the second derivative. What is it?
12x squared minus
It's 24x to the first, right? Okay. Do I set up regions? Do I solve the zeros? Do I set up regions? Or what do I do now? Okay, so building off of these, what's special about those points? That's where the original graph does what?
Changes. Or well, sorry.
The derivative is 0 implies the graph went
Flat.
flat, okay? Now that could be went flat and not a max, went flat and a min, or a max, went flat and a min. Could be lots of things. So now we're using the second derivative to go a little more and say what's going on at that flat spot. So this is, you test the derivative at the points, at the critical numbers, not intervals. So what is y double at 0? 0. Now that's actually inconclusive. You need a sign. So that's going to sink. We'll deal with that in a second. What about y double at the other critical number 3?
36.
So let's see. Like 9. What's 12 times 9? What, 108? It's already 36, you know?
Yeah.
Oh, okay. Thanks. Good job. 72. All right, I'm with you. 36. Great. Now, what does that mean?
It's positive.
Okay, it's positive, so that's good. What's going on then at 3 graphically, considering these two things I found?
It's a relative min
Why is it a min?
because it's
Smile.
because it's
Smiling?
no because it's concave up.
Okay,
And
yes.
It's 0.
It's flat and concave up. Smiling. I like that. And therefore, that is a min. It helps me to draw it, but if you're fine, you're not fine. Okay, so in terms of the conclusion and how it should be worded, both in good math and specifically for the AP, you would say, it says find the x, so I don't need the y coordinate. I'm just going to cite the x here. Y has a min at x equal
3.
3, because now the second derivative test requires 2 pieces of evidence. It's not enough to just say concave up, because isn't that point concave up? But that's not a min. So you need concave up with the flat. So let's cite the evidence, because y prime at
3.
3 equals 0 and
Y double.
is positive or is greater than 0. Okay? The second derivative test should cite 2 pieces of evidence. Any questions on the second derivative test?
Nope.
Going back then, it said use the second derivative if possible, the first derivative test otherwise. The first derivative test never fails. It works in every case, it's even in corners and cusps, and so that's your backup. So at the other point, as far as add x equals 0, we're going to have to back up and go back to the first derivative test. How do I run the first derivative test?
You create something.
Yeah, a sign test around 0. Before 0, what's the first derivative? Or sorry, yeah, before 0,
Negative.
it's negative infinity. Do we agree with that? Do I agree with that? I think I agree with it. It's negative. And after 0, what's the sign? Positive. Okay? It's actually, yeah, that's fine. Positive. I should have probably had 3 in here, but that's okay. So as far as what's happening specifically at x equals 0, there is a what? Relative min. Remember, this means slope decreasing, then increasing. And so there's a min.
Mr. What was into the first derivative? It is negative.
Oh, poop. Oh, no. So, thank you. I did not. I actually just assumed what a dummy I am. I agree. 1 yields a negative. So what happened at 0 then? It was decreasing before 0. It went flat, and then it went back to decreasing. So what was happening at 0? Nothing. Nothing is happening at 0 in terms of extrema. There is no extrema. I suppose you could leave it out. Yeah, there is no extrema at x equals 0. It went flat. Kind of like an x cubed would, but it didn't have an extrema.
Is there like an advantage to using both of the second derivative test and the first, or could we just do like the first every time basically and do the sign test?
Good question. In terms of implicit, let me say it this way. In terms of implicit derivatives, I'm so glad you asked that. Imagine a sign test on an implicit derivative that is a function of both variables. You then have to do a sign test in 2 dimensions, x sign changes versus y sign changes, and it's a freaking mess. And so second derivative test is definitely better in implicit cases. And so that's why you focus on second derivative test, the biggest use. I'm so glad you asked that. It's a great question. Okay. Optimization problems. Switching gears, this is also a derivative application problem. This is useful in a lot of applications. Business calc, for example, you do a lot of optimization problems. So let's talk an optimization problem. Say a rancher has 200 feet of fencing to enclose 2 adjacent rectangular corrals. I didn't say so, but it's just in an open field with nothing there yet. Find the dimensions of the corrals that yield maximum area. So you're starting with this blank space, and you're making 2 adjacent rectangular, adjacent meaning next to. Let's also assume they're of the same size. Okay. You have 200 meters or feet of fencing to make those lines. How shall you make them? What would you do after you've got a little doodle there?
I would call each vertical line.
Okay. Let's identify variable. H is okay. H is fine. It's arbitrary, but we could call that H. What about the others? X, okay, X. Each little one X, or the whole X and then half X. I don't really care. Each little one X. Okay, sounds good. All right, we've identified our variables in the picture. That's good. That's going to make our equations a little more logical to somebody reading them. Now what?
You set up equations. 200 is equal to 4x.
Okay, to me now that would be putting the cart before the horse. What's the question? What are we trying to do?
Find the dimensions.
Dimensions that maximize
Area.
So we should probably start with area. What's the area? That which you're trying to optimize, you need an equation for it. Okay, what is an equation for the area? 2x for the base times h for the y. Okay. Now, why not just start cracking with that?
Because you don't know meter.
Yeah, how many variables?
Those.
I see 3 actually.
Oh, actually.
A, X, and H, that's 3. So 3 variables is bad. If we can get it down to 2, that's good. Okay. Don't get these confused with related rates problem. We're not differentiating with respect to time. There's no time here. All right. I have a lot of people that get those two confused. It's not a related rates problem. It's all about how these variables relate. So getting it down to 2. What's another? Now is where we find an other relationship to get it down to 2 variables. Now that's where 200 comes in. So
200 is equal.
200 is equal to 4x plus 3 h's. That's all the fence we have to work with, and that's what we need to come up with. Wait.
Yes.
Solve for h or solve for x? What do you want to do?
X.
Solve for h? Okay. H is 200 minus 4x over 3, or if you like, 200 thirds. I don't know which one's easier to use. Whatever. So if I put that in there, then my new equation, sub in, is area is 2x times 200 thirds minus 4 thirds x, or what, 400
X.
thirds x minus 8 thirds x squared. Oui.
Yeah.
All right. Now we want to find the relative max or min.
We want
Relative max. Okay, you might want a relative min if you're trying to minimize cost or something like that. Okay, how do you do that?
take the derivative.
Take the derivative. What notation do you want to use for your derivative? A prime is fine. DADX is fine, whichever you prefer. A prime, what is it? 400 over 3 minus
16 over
16 over 3x. How many critical numbers will we be getting?
1.
1. And that critical number is 400 thirds times 3/16 or what? Or what? 25. Now the dimensions of the pen. To answer the question, make sure you answer. Actually, let's verify. I'm not picking that you prove it to me that's a match, but you should look. Before 25, say it 1 or 0, positive or negative?
Positive.
Positive. After 25, say it a billion. Negative, and therefore there must be a
0.
max if it went positive to negative. So it is a max. I did look. Max, check. All right, then answer the question. The dimensions. Each pen will be 25 units by, oh yeah, what is it? 100 over 3. I agree. 100 over 3 feet. Oui, oui.
Yep.
Is that looking familiar?
Yep.
Is that looking like fun?
Yeah.
Yes.
All right. Okay. Turn it to the back. Let's talk curve sketching and graphic relationships, and then we'll be good. Let's say I give a table of f prime and f double prime. Sorry about the iffiness on this. It's a little cloudy, but it'll be okay, I imagine. So, we're going to sketch this. I have no idea what A and B are, whether they're positive and negative, so it kind of is hard to put them on the x-axis, but let's just say there's A and B. What do you say? Likewise, there's no y value shown, so I don't really know where to put it in relation to the x-axis, above or below, so again, I'll just rough it in above. What do you say? Tell me, what's going in from A? Whoa, wait a second. I guess I kind of do know, don't I? I'm dumb. What's that say? Look at the B. Wait a second.
Oh, my eye.
Wait a second. A to B, B to 0, and does that say 0 to B?
Yeah.
And A has to be less than 0.
A is definitely less than B.
So A has to be less than 0.
Yeah, this is what's cooking me up. By transitivity, B is less than 0. But also by transitivity, B is
Greater than initial and B final.
Yeah, let's do P1 and P2.
That's and A.
let's call this C. What do you say? Wow, that's crazy. But this book is known for its errors. So here we go. A and B are both negative, yes?
Yes.
And C is somewhere positive. All right, great. From A to B, tell me two things about the graph, my friends.
Slope is negative and it's concave.
Slope is negative, concave up. So what would that look like? Something like this.
Yeah.
At B, slope is 0. There's a horizontal tangent, and it's concave up. Smiling. So positive. From B to 0, what's going on? Increasing concave up.
Changing from a smirk.
At 0, what's going on? Sorry about that.
F prime is 3.
F prime is 3, and what am I looking ahead? What's going to happen in terms of the second derivative? It's going from positive to negative, so I'm going to have an inflection point. I'm about to have an inflection point. What about from 0 to C?
From 0 to C.
Increasing or decreasing?
Increasing.
Concave up or concave down?
Non-hand down.
Concave down. Okay. Something like that. We?
Yeah.
Okay.
I thought that negative was equal sign.
Oh no, it's a little fuzzy, to be sure. Try this one on your own, and I'm going to try it on my own, and I want to start to get a feel for just how doggone good you are.
I don't know what it is.
Oh,
My eye.
that's a cop-out. You know darn well what it says. You just don't want to do it.
No, it's easy. It's just.
Which part? All of it. Come on. This shows the graph of f prime.
Okay.
F prime has horizontal tangents at -1, 3, and 5.
It's negative.
Minimum.
Oh,
F
negative 4.
Okay. And A, find all values of x in the region where f attains a relative minimum.
Minimum.
Justify your answer. You bet it says minimum.
F attains or F prime?
F, where f attains.
Sweet.
This equals.
Okay, well, f will attain a min where?
Oh, the 4 has a 4.
F prime equals 0 and F double prime equals 0.
Oh, well, you're, okay, never mind. Go ahead, I'll let you finish. I'll shush you.
Got it.
By first derivative test, you get a min where f prime goes negative to positive and probably 0 in between, but mostly negative to positive is what has to happen. Okay. Pause for A, make sure you're on the right track. So, how many solutions to A? 1. F has a relative min at x equals 1 because F prime changes negative to positive there. Okay. Yes, it equals 0 there, but you do not have to say that. That's not part of the first derivative test. That just tells you where to start looking. It can cost you on certain AP tests because it is not part of the first derivative condition.
If you just
Saying
second
either
it.
needs to be said. How come I'm not giving the x and the y? Is it
Find all
possible to
values
find
of
the y
x.
values on the original function? No, not even possible to give the y. Okay. All right, B, what'd you say? F has a
Max.
relative max at x equal negative. Oh, I didn't see the scale. 2. Good point. Because F prime
Positive.
changes positive to
Negative.
negative. What if you just said relative max at x equal -2?
You didn't justify it.
You would lose points on the AP test. And that's because a lot of people would say F prime has a relative max at x equal -2. Now, are we talking about F prime's maximums? No, F has a relative max. So, just to be clear, you should say F has a relative max. You should never just say there is a relative max. You need to say what has relative max. You should never say it has a relative max. That will never do. Pronouns are never allowed. And obviously it's not F prime has a relative max. That's ridiculous. Okay, have you done the last one?
Yeah.
Okay, this requires you to make a bit of a judgment call. From -4 to 2, what's happening with F? Sorry, from -4 to -2, excuse me. From -4 to -2, what's happening with F? It is increasing. F is increasing. How do you know that?
Because F prime is positive.
Okay, so it's increasing, then
Decreasing.
decreasing. Tell me this, trusting your eyes, Did it decrease more than it increased?
Yeah.
Relative area wise, okay. So it feels like we just lost a lot. What about this? F is
Increasing.
increasing, then
Increasing.
increasing. All right. Golly, this would be hard to justify. In retrospect, I need to give you a little more time because if you're going to do this well, it's going to take a while. Do you want to review it? Do you know what you're doing? Okay. All right, absolute. Remember we talked Friday about absolute extrema. Friday is a little more. It is that absolute extrema. You first are going to kind of lay out your thesis for the problem. Absolute extrema only occur at endpoints or critical points. Okay? Now the endpoints are most definitely x equal -4 and 7. The critical points first tell the reader, hey, this is where I'm finding them. What are the critical points and how do you know?
Critical points on red.
F prime equals 0 at
-2,
-2,
1, and 5.
1, and 5. All right. Now, in terms of actually being able to find these, this problem is not set up to be able to find them. I would need areas given or an integral to be able to find the areas. So let's play a little fast and loose with the changes. Between these, what is the greatest? F at which is the absolute greatest? F at 7 is the absolute max. Basically, if we had everything we needed, we could set up integrals saying the integral from 5 to 7 is positive and therefore greater than it. It would take a mess. We'll get there later, but for now, that's kind of what I wanted to review both of those elements. All right? Okay. Do this one. This should take 30 seconds. First derivative positive implies?
Increasing.
Second derivative positive implies?
Concave up.
At what point is it increasing concave up?
B.
B, I agree. C is increasing, but it feels like concave down. Don't you agree?
Yep.
Okay. All right. I guess that's it. Is that it? Okay. All right. 4 more questions. Do you still have, I did post the keys, I think, unless I screwed it up. So I think you should have had keys for some of the stuff. Can we just call it good on review 5 because half the people or more turned it in already and start with questions on review 6? Do you have any questions on review 6? Review 6 is the best review of the review. Some of you have already turned it in, but only a handful.
Page 158, number 19.
Page 158,
It
19.
doesn't have a box number.
Okay. That I can work with.
It's like a double quad, where you, like the column is almost different than what
Okay. Yes.
Number 15 and the supplemental.
15 is the supplemental number. I'm sorry, say that again. 15 on the supplemental on the back. Okay. Page 158, number 19. Here we go. I remind you to make these corrections in ink so I know where people are having trouble.
Just recommend vinegar, use the restroom.
Sure. Okay, so for 158, number 19, the classic sand problem. You have sand coming in, making a conical pile. Depending on the viscosity of the material, it would make different kinds of conical pile, whether it's sticky. It would tend to be a little thinner, and if it's slidey, then it would be wider. So at any rate, we've got sand here. It says, all right. Now I don't know how Miss Cannon taught you, but this is what I like to see. I won't grade you on it, but to me this is good work. On such a related rates problem, you should establish what's given. If sand is coming in at a rate of 10 cubic feet per minute, then you need to be able to put that into calculus. What does that imply? All right. Now, on many AP problems, that would be the first point. Please be intentional. Because it's coming in, volume is changing in an increasing way, and so you give me the sign, even if it's positive, 10 cubic feet per, it was 2 per minute, okay. All right, the other given they throw in there is that the diameter of the base is approximately 3 times the altitude. Altitude is the same as the height in this case, 3 times the altitude. Okay, as far as what you want, we want to know if the sand is coming in and the volume is changing, at what rate is the height changing when height is 15. Please obviously read that carefully. That's just the instant. That doesn't mean height is constantly 15. That just means when to look. All right. What did you do after that? In order to find the HDT and use dVdt, we probably need a V equation. What's an equation for volume of a cone? Okay. Now, would you go to substitute to get it down to 2 variables, or did you use 3? Substitute is great. I took this and trying to get R in there. That means 2 R's is 3H, yeah? Considering I want dHdt, I suppose I want H to stay, so I probably want to sub for R, yeah? So R is 3 halves H. If I then sub that in, I over 3 halves H gets squared times H. I get pi over 3 times 9/4 H cubed, or 3 pi over 4 H cubed for a volume equation, yeah? Okay. At that point, you're probably home free. Differentiate. Take the derivative well with respect to time. What's the derivative with respect to time? 3 pi over 4 stays, and 3h squared times the derivative variable with respect to time. dHdt. Plug in and solve, or solve and plug in. It should be good. Okay. 54 in the book versus me. Let me figure out what that means. 54 in the book versus what I have. Oh, cool. All right. So, estimate the square root of 11. There are actually whole books dedicated to not just calculus, but using calculus for approximation in real life. It's at the end of this year, we did a list at the end of it. There are like 11 different approximation problems to use in the calculus between 1 and 2, and that's just getting the start. Did you get started and have trouble later, or was it getting started that was the problem?
Like in the book, it doesn't have the phrase like use a tangent line.
Yeah, it's not even a problem. It's just using implicit differentiation. So I was really confused.
Yeah. So ignore their problem and just treat it like this. Estimate the square root of 11 with a tangent. Does that get you going? And I apologize for the terrible warning. Or shall we still walk through it? Still walk through it. Okay. Now, back in the day before calculus, you would estimate the square root of 11 with, I'll try 3.2 times itself. And then I'll try 3.3 times itself. And if I want to get more exact, then I'll try 3.23 times itself. It's pretty tedious, yeah? The idea here is that you're going to say, well, I know that the square root function looks like this. And while I don't know exactly what the square root of 11 is, I do know a point nearby, 9. And if I just say, well, based on how it's changing at that point, I could use its rate of change to extrapolate. Well, if it kept changing at the same rate, which obviously it curves, so it doesn't. But if it did, by the time it went 2 more units over, or delta 2, the height would be this much. At the end of the day, then, it amounts to this. You make a tangent line at 9, 3, and then plug 11 in to the tangent line, which would be a pretty good approximation. The tangent line would be a little more, I expect, than the true value, but that's okay. So, to get a tangent line, you need a point. When you put 9 into the square root function, you get a 3. You need a slope. How do you find the slope or how it's changing at the good point 9? Derivative. Okay, y prime is 1 over 2 root x at 9. The rate of change at that point is 1/6, yes? Okay, the tangent line then is y minus 3 equals 1/6 x minus 9. Are you with me?
Yeah.
Therefore, y is 3 plus 1/6 x minus 9. Pause for a, do you understand how beautiful that is? Moment. Y, based on where it's at 3, y would be 3 plus this. This is change in y over change in x. I would expect y to change 1 unit for every x change of 6 units. Unfortunately, in this case, when I put in 11, x is actually only changing 2 units, so y will only change by 1/3, or actually, did I say that right? Yeah, 1/3, and so y would be 3 plus that 1/3, and y is 3 1/3. Follow? Okay, 15, and supplement on the back. Are those are those related or separate?
Separate.
Oh, okay. Sorry, I misunderstood.
Yeah.
First of all, 15. I don't know if they simplified. Did they simplify their? I don't require that you simplify. So if your answer doesn't match the same form as theirs, I'm good. Is that the question, or is the question let's do the derivative?
No, it's just simplifying.
Yeah, I don't care. So as long as you could, on a multiple choice, find the exact equal, then you're good. And then the supplement of the back. The derivative problem? Yes? Okay, check this out. If you checked continuity, hoping, hey, maybe it's not even continuous there and I'll just be done, the derivative doesn't exist because of discontinuity, I think you'll find that it was continuous. Yes?
Yeah.
All right, so now the question is, does it hand off smoothly in slope at the point 3, 4? I know they hand off and it looks like this line and then parabola, but is it smooth? This is what the work should look like. You want to create, did you use alternate or first definition?
Alternate.
Alternate, okay, alternate sounds good. You create an x and find the slope between on that side. Doesn't that mean x is approaching 3 from the negative side? That's 3, x minus 3. In terms of the branch then you're going to be on this branch, so it's going to be 3 plus x minus f at, why am I saying 3?
Yeah, why should they
It should be 1, yeah? Sorry. No wonder you're confused. Okay, f at 1, what is f at 1? According to the line, it would be 4. Over x minus 1. Howie, gee, sorry, I'm going too fast on big counts. X minus 4 over x minus 1 gives 1. Then didn't we kind of know the slope over here was 1? There's linear. Okay, in terms of the right-hand side, if you create a point on the other side of 1, then the limit as x approaches 1 from the right side is more like the parabola. Have a good day. Make sure I get this one by the end of the day. All the others you can keep.
So 5 and 6.
5 and 6 are definitely due today, yes. X plus squared plus 3 minus 4. This actually, after canceling out, equals 2, because the limits are unequal, the gradient's not existing. Okay? Have a great day. See you at 7th if you have more questions, or after school.
Maker.
Hi, Doc.
I have a quick question.
Sure.
Where is the one, remember?
We don't have.
Yeah, that's kind of why I wanted to go there.
I want a horizontal strip.
Oh, so I
No, they will consistently, a gap is 45, and now a gap is 60. That's so. I guess what I would say, exactly. I would say choose a scale and then rotate all the points using that scale.
So how I normally do it, and like
Actually, you know what?
when I find like the shift or whatever, I put that number down first. Is that how you would do it,
You
or
had the lines, you know what
it's kind of hard, like when it has a shape?
I agree, and even more so in science when they're not pretty consistent.
Yeah.
I'll make up a sheet. Actually, I just made one for AB that I handed out on how I want things done, and we'll go over tomorrow. Okay?
Thank you.
You bet. Have a good day.
Sure.
Yes.
I have a question, because you wrote scale here.
Yeah, that's also with that's I'll go over tomorrow.
Okay,
Okay.
okay, sounds good.
Okay. Oops, I forgot to pause.